Hello, students. Moving into 13.4. There are 5 sections left in the book. We're just rocking and rolling now. So let's recap so far. We've got 13.1, which talks about measuring lines. That's one dimensional. You put that together with a line going in the other direction, you have area, which is two-dimensional. Now, again, Pythagorean theorem was thrown in. Truly, I think this could have been switched with 13.2 because it measures a length, but they did use a whole lot of it in measuring things like areas. And because the Pythagorean theorem typically refers to areas on the squares, I can understand the idea. So you bring that now to 13.4, and we're going to talk about area, but not of two-dimensional shapes, area of three-dimensional shapes. And that's where things get, for some students, a little bit tricky. It's a little harder to visualize. We'll be bringing in some 3D shapes into class to kind of understand what this is, but you can see these in real life. And the idea would be something like a cereal box. If you cut all of the pieces away in a cereal box, just as they are, you will end up with a number of smaller polygons. And I think that's the piece I want to talk about here is when we're talking about these shapes, we're going to turn them into shapes we already know. So we may not have this as like what's the area of this shape, but what we do is we unfold it. So when you have this cereal box, think of the top, just kind of fold it up or cut it. Okay. Now you got to be careful here because when you actually tear apart a cereal box, there are additional pieces that are in there to be glued together to provide stability. But when you just cut right down the edges, this is the shape you're going to get. And that's what we're referring to. What is the area of the surface? And what that means is how much would it take to cover this surface with little squares? So we'd have to cover the front of the cereal box, and we'd have to cover the back of the cereal box, right? Now, what's great is when we're doing a right prism, those two shapes are identical. So again, it's like, oh, cool. I don't need to think of them as two separate pieces. Let's continue. We also then have the top and the bottom. And once again, those two shapes, their measurements are identical. And finally, let's see here. What do I want to choose? Maybe I'll choose green. Then we have the sides. We have like the left side and the right side. And once again, those are the same. So what you're going to notice is when we start looking at how would I create this? Look at the individual shapes that are made. This is just a rectangle. And guess what? It's the exact same dimensions as this rectangle. So while they give you numeric dimensions, which means you could just come over here and multiply to find the area of each of those components, we also could do this with, say, this would be like the height of the cereal box. And this would be, say, the length of the cereal box, and this would be the width of the cereal box, something along those lines. And those could be interchangeable, if you will. So when we think about it, we need two of the front and back, and the front and back would be height times length, and I need two of them. And then I need two of the sides. But what are the side pieces? That's the height times the width, plus two height times width, plus what else? Plus two of these, which is plus two length times width, and everything seems fine. Let me just share one thing with you. There's nothing wrong with this idea, but if we write it out and we kind of take a moment here, we could say, okay, I have two length times W. That right there is 2 times the area of the base. Remember, the base would be kind of this what it's sitting on, if you will. Okay. So I have 2 times length times W plus then I have 2 height times length and 2 height times width. Now, what I'm going to do is I'm going to factor this out to get a 2 length plus 2 width, and I multiply that by the height. And there's a reason for that. Okay, I want you to go along this journey with me here. If you were looking at this box and I removed, I'm going to try white space here. I'm really hoping this works. And I'd cut it all open like this, and you look and you see, oh, I see 6 different rectangles. I completely agree with you. Now, if I remove what we had over here, which was the um, 2 times the area of the base, if I remove those pieces, I'm going to white them out here. Let's see if this helps. Visually, this always helped me when I could see it this way. Okay, and I'll even remove all the other measurements just so you don't kind of get those mixed into play here. What shape do you have? Now you may look at that and say, oh, Scott's 4 rectangles. I'm not disagreeing with you. You did that. That is perfect. But let me do this then. If that's what you see is 4 rectangles, what do you see now? I hope that you see what I see, which is 1 rectangle. And that rectangle is composed of the length and a width and a length and a width, which is 2 length plus 2 width. What is that? That is actually the perimeter of that base. That base shape is a single rectangle, and it's a rectangle that is length times width. So the perimeter of that is here. And then this component over here is just the height. So when you have this right here, you really have the perimeter of your base times the height. So take a look. You have 2 times the area of your base plus the perimeter of your base times the height. That is probably the quickest and easiest way to think about this. Instead, it's not bad. You can always break it down into all those rectangles. This just gives you a technique that allows you to do it, what I believe to be a little bit quicker. So I don't bring the height into play. I bring the height into play 1 time. The rest of it is all length times width. Tell me what my base is. There's a really cool way to think about things, and I think it makes things a lot easier as we go forward. So when I look at this shape, right? When I look at this shape, which is a cube, okay? So notice here, they're saying, well, I could look at the cube and I could find the area of one of these and realize they're all the same. You're completely correct. But what you could also do is, let's just check it with what we just talked about. Let's say that this thing right here is the base. The area of the base is S times S. Now I have a top and a bottom. That's the 2S. Again, I'm going to link this back to what we just had. 2 area of the base plus perimeter of the base times the height. Okay. Plus, now let's look at the top and let's say, what's the perimeter? That's S plus S plus S plus S. The perimeter is 4 S's. The height, again, because it's a cube, is S. So I end up with 2S squared plus 4S squared, and my end result is 6S squared. And again, why am I showing this and not saying just find one of them and multiply by 6? Because this only works, let's see here. This only works for cubes. So I don't personally like memorizing 16 different formulas. If I can do one formula and it all connects, I feel like I'm better off. So to me, this one's just better. Okay. Now you'll notice they do give you a net shape. The idea of the net is, can I unfold this box? But just realize the one they showed above for the cereal box, I could have done the same thing. I could have had something like this. And one of these up here and one of these down here. I could have had that. Again, these are 2 nets. As long as it can be connected into that shape, you're good. So if you choose to see it a little bit different, don't think that that's wrong. Just make sure it does fold up into the shape we're looking at. Okay. So what we're going to do is, once again, if I had a weird shape like a pentagon on top and bottom, then I have the area of the top. Now, I think in this case, the book did change. They're using 2B, which is the area of the base, which is fine. So they can use A for everything else, which is fine. I'll tweak mine to match the book so that if you're studying, it matches. So they have the top and the bottom. That's 2 area of the base plus. Now, this is where, again, take a look and see if you can spot it. What remains when I unfold everything into that net is one entire rectangle. And the rectangle is made up of what? The rectangle is made up of, oops, I gotta switch back to my pen. There's one side, there's two side, there's three side, there's four side, there's five side. Right here is the perimeter all the way across. You can also think of this rectangle has to wrap around the outside of this pentagon, which is why it's the perimeter. And it's the perimeter times the height. So again, there's your overall formula. If you have a right prism, okay? So if you want to find the right prism, I always start with the base. The base is the same as the base down here. That's a 3, 4, 5. So if you want, you can say what's the area of the base and what's the perimeter of the base. The area of the base is length times, it's a triangle, so it's 1/2. The base of that triangle, which is 3, the height, which is 4, so 3 times 4. 3 times 4 is 12, and half of that is 6. And these are centimeters squared. The perimeter is 3 plus 4 plus 5, so that's 9, 10, 11, 12. So it's 12 centimeters. So the overall surface area is 2 times 6 centimeters squared plus 12 times 10 centimeters squared. So this is 12 plus your choice. You can multiply them out or you can factor it. It's up to you. I'll multiply them out this time. 120 gives me 132 square centimeters. Okay. That's the idea. What kind of shape? Prisms. Right prisms. Okay. All right. Surface area of a cylinder. What's a cylinder? Well, let's take a look. A cylinder is basically like taking a prism and just keep adding more and more edges. So it's almost like a prism with an infinite number of edges. Now, if you have one of these at home, you can do this, but I urge you to be very, very careful, as cutting metal will be kind of a pain. But if you think about it here, you'd have a piece on top, and so you fold it up, and then you'd kind of unroll down here. You'd have another piece on the bottom if you open that up. And then as you unroll the side, you'd get something like this. And if you think about it, think about this top is going to wrap around that. So think a piece of paper of a, like if you cut down a toilet paper roll or a paper towel roll and you unfolded it, what are you going to have? You're going to have a rectangle. Okay, so now what do I have here? I have a base, the area of the base. There's another base. And right here, that's the perimeter, and this is the height. But in this case, it's the perimeter of a circle, and the perimeter is the circumference, which is 2 pi r. And the base is the area of a circle, which is pi r squared. So overall, the surface area of a circular cylinder is 2 pi r squared. Remember, that's our two bases, plus the perimeter, which is 2 pi r, because it's the circumference, times h. And this is p times h. So it's the exact same formula. So remember that. Do you have to memorize this one? I don't personally think you do, because that seems silly. If you know the same thing from a prism and a cylinder are effectively the same shapes. One is polygons, one is made with circle. Okay. And yes, you could factor this out if you really wanted to. I mean, I'll leave that up to you. If maybe if you're computing, it's a tiny bit easier, but if you factor out a 2, a pi, and an r, you're left with r plus h. But again, I don't personally think that's necessarily critical. All right, so there you go. And there it is, says it right there. Surface area is 2 pi r squared plus 2 pi r h. Okay, now let's get down to a pyramid. Yes, so a pyramid now has these side areas. Let's see if we can get over here to a net of a pyramid. It kind of does help. Here we go. Here's a net of a pyramid. So now that's kind of interesting, because now we're going to have some slightly different components. And that's because I'm going to have triangles here, right? I will have triangles here. How many triangles? Well, I technically have 4 triangles. Each triangle is this base length, which is B, times what is known as the slant height. And that's the L, that's the slant height, and that divided by 2. And I have 4 of those. Okay. And then I have this base, but in this case, I only have one base. So really it's base plus 4 times B times L over 2. Okay, but let's do this. Let's do this. This net, there's nothing wrong with this net, to be honest, the way they have it. But if I erase some of this stuff here, you also could think of just making that same kind of walk around this shape. If you walk around this shape, right, there is B, there's a B, that's 2B, there's 3, that's 3 B's, and going all the way around the shape is 4 B's. So 4 B's, when you see 4 B's, is actually the perimeter of the base. So the overall formula for the surface area of this is base plus the perimeter times the slant height divided by 2. And if you go back to 13.3, where we did Pythagorean theorem, you may not know the slant height, but given your shape, you could find it using the Pythagorean theorem. So if you're not given the slant height, you oftentimes can find the slant height. Just make sure this is the slant height, is what we call it. And that's, again, it's not the overall height of the right square pyramid. The height of the right square pyramid would be from this point straight down, making a right angle with the base. This one is slanted. So again, the difference, if you think about like a mountaintop or something like that, right? If you go hiking up the mountaintop, you're heading up this direction. You have to walk for 3 miles, right? That doesn't mean that the height of the mountain is 3 miles, right? Maybe the mountain's only 9,000 feet high. Well, that's, a little bit less than 2 miles high, but you had to walk for 3 miles to get up there. Or maybe you had to walk more. Maybe you had to walk 8 miles to get up there. So that's the difference between the slant height and the true height. That's why maybe some of you are like, isn't it just the same? It's not the same. It's not the same. All right. Yeah, so here's an example. And again, all they're going to do, you're just going to see what's the area of the base. Well, it's a right square pyramid. So you just multiply 4 times 4 is your base. And then your perimeter is, again, 4 times 4. Because I have, 4 plus 4 plus 4 plus 4. So I get 4 times 4. And I do it, which I think is strange here because they give you that good formula and then they show it to you in a completely different way. Not that this is bad. You could break it up into 4 triangles if you wanted to. But if you really want to use what's in the B plus 1/2 perimeter times length, slant height, then the base would be 16 because it's 4 times 4. The perimeter would be 16 and the slant height would be 5. Okay. Again, what's nice about this is you can just multiply through. So you have 16, half of 16 is 8, and 8 times 5 is 40. So I also get 56 centimeters squared, but I didn't do 4 triangles. I did the perimeter of 1, making 1 entire shape. All right. Very cool. So prism, cylinder, those go together. Pyramid, now think about it here. Pyramid, what's a pyramid going to match up with? And if you said a cone, you nailed it. Think about pyramids with bases that get larger and larger and larger. Eventually, you get to a shape that looks like a cone. So let's go back to it. What should we have? We should have the area of the base plus 1/2 perimeter times length. And the length that we're talking about here is the slant height. Okay. So the base, that's going to be pi r squared. The perimeter is going to be the perimeter of this circle, which is the circumference, which is 2 pi r. So when I bring this down, I get 1/2 times 2 pi r times the slant height. And that means my final result, my surface area, would be pi r squared. That makes sense. But now here's what's great. You have a 1/2 times the 2. Those go away. So at the end, all you're left with is plus pi r L. Now, if you really wanted to, yes, you could factor out a pi r, and it leaves you with r plus the slant height. If you think that that's a little bit easier, go for it. I think they're roughly the same. And again, it all comes back to this formula we saw first. So there we go. Awesome blossom. Again, all of these turn into nets, every one of them. If you have a pyramid, you're going to have individual. Maybe it's the base is a 60-gon. You're going to have 60 very, very tiny little triangles. Here, with the right circular cone, you're actually going to have infinitely many triangles that are just infinitesimally small. So anyway, that's the that's the final piece. Very cool. Very cool. So when they say find the surface area, let's see here. Did they actually do it? Pi times 3. Yeah, they actually did it in this case. So just kind of following along. I have my slant height here, which is 5. My radius, my radius is 3. So I have pi times 3 squared plus pi times the radius, which is 3 times the height, which is 15. And 15 pies plus 9 pies is 24 pies. And these are all centimeters. So because it's area, I end with centimeters squared. All right. So in terms of overall units, this one's actually a pretty short unit. I know it looks formulaically big. Like I said, there's going to be a lot of formulas. I'm not asking you to have them all memorized, but I hope you see the connection that it actually isn't that bad. You're breaking it up into pieces. This one is a little bit beyond the scope of this class, but it's a fantastic formula. And if you had taken calculus, you might be able to get to something like this. And I'll show a connection later. Again, if you've had calculus, that's fantastic. If not, that's perfectly fine for what we're doing. You just need to kind of know the surface area of a sphere is 4 pi r squared. Now, what's interesting is the pi r squared is a circle. It's the area of a circle, just kind of by itself. So if you think about that, and you think about the way a sphere is designed, a sphere has a radius from the center to the outside edge. The circle, what we would call a great circle, because it would go through the center of the circle. And again, you could have other circles that are kind of like up here. You like cut them off and you're like, oh, that's a circle up there, but it didn't go through the center of the sphere. And so therefore we don't call it a great circle. But one of these great circles, the area of that great circle is pi r squared. And what's great is if you want to coat the surface of this sphere with something, maybe paper, maybe you want to dip it into something and see how much do I have to kind of get it on there, you would say it's actually 4 of these great circles. So 4 pi r squared. All right. And that's it. So really one formula for prisms, one formula for pyramids, and one formula for a sphere. That takes us into the homework. All right. Let me know if you have questions, and we'll do some of this stuff in class, of course. All right, off you go.